We're continuing our study of what is the derivative and how can it possibly, how could we possibly deal with the derivatives of certain types of functions? All right, so as a sort of recap, does anyone remember the limit definition of the derivative that we covered last week? Just sort of off the top of your head, more or less. You can give me either one. Yeah, it was basically the instantaneous rate of change. We had that really big limit. It was like one of our definitions was the limit as h goes to 0 of f of x plus h minus f of x all over h. All of these big algebraic expressions that we had to work with. So that's what we learned about last time. So basically this definition, f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So this is just a recap of what we did last week. All right, and this definition is really nice if you're really good at algebra. It is tedious, I will admit, especially if we were working with more complicated functions. Really, the examples that we worked with, we were mainly talking about, for example, something like x squared or 4x squared. We even did a square root one, for example. But we know that there's much more complicated polynomials and things that aren't even polynomials. We have like sine functions, cosine functions, all these trig functions and everything like that. This unit is going to talk about how do we get the derivatives of those. And we're not really going to talk about this limit definition as much. We're not going to use it very often. We may use it to prove a couple of our theorems, but overall, we're not going to be focusing too much on it anymore. All right, so let's go ahead and talk about our first theorem. Let C be a real number constant. So whatever C is, it's a fixed real number. Then let's talk about notation here. Here we see this notation d dx that I have right here. Let's talk about what that notation means. So for us, that notation is just basically going to represent the derivative of blank in respect to x. So if I read this first one, d dx of c, this is saying the derivative of my constant c in respect to x. Or often you're just going to hear me say the derivative of whatever. So I'm going to break this down into two parts. For right now, let's not worry too much about the phrase in respect to x. And let's worry for right now about the derivative of whatever. So I claim that you could very quickly interpret this first statement on the left. The derivative of a constant is equal to 0. Why is that true? And why am I saying that you could probably have figured this out with enough time? Well, first off, what was that thing I was saying the derivative is equivalent to? Start with an S. Slope. So we can think of the derivative almost like the slope of the function. Of course, there's a little bit more nuances. We use slope for flat lines, but then we're using derivative for any curved function. If I have a function that is just a constant, like y is equal to 20, what does that graph look like? Yeah, it's a flat line. So if I look at any constant function, like 12, 24, whatever your favorite number is, pi, the graph of that function is just a flat line. What is the slope of a flat line? 0. So that is why the derivative of a constant is always 0. The slope of a constant function is always 0, hence the derivative is always 0. Hence, you've just sort of derived this first expression already for me. What about this second one? The derivative of x is 1. Again, this is also something I claim that you would have been able to derive after a while. Why is this one true, or how could you sort of justify this statement here? You can follow the same process. What does the function y is equal to x look like? Basically just like a diagonal, right? Like if this is my Cartesian plane, imagine that it was completely straight. This is the function y is equal to x. So what is the slope of the function y is equal to x? 1. Because we remember for a linear function, things that are aligned, it always has a form y is equal to mx plus b. So if I'm looking at y is equal to x, you could write this as 1x plus 0. That is a slope of 1. So from this, we know that the derivative of a constant is 0, and the derivative of a plane x is 1. This is our first theorem. And really, if you wanted to, you could have also proven this using our limit definition that I showed earlier. You'd actually get the exact same result. But we're trying to think of this a little bit more visually at first. So these are probably the derivatives that you would want me to give you, where I said y is equal to 12, give me the derivative. You would say instantly 0, it's a constant. All right, so we have our first theorem for today. Let's go ahead and move on. So let n be a real number. So n is any real number that you can think of. Let's say I want the derivative of x to the n power. I'm going to have y'all write out this first, and then I'm going to use the phrase that we always talk about for this particular one. And this theorem actually has a very particular name. This theorem is actually called the power rule for derivatives. So I'll go ahead and write that up here. As I said, this is often called the power rule. So the derivative of x to the n power, where n is a number, is n times x to the n minus 1. But you're rarely going to hear me say that directly like that. Rather, you're going to hear me call the power rule saying, if I want the derivative of x to a power, we're going to drop the power and reduce it by 1. For example, let's say I had f of x is equal to x to the 4th power. The power rule tells us that the derivative of this function, f prime, is I drop down the power. So I take this 4 and bring it down to give me 4x, and then reduce the power by 1. So 4 minus 1, we get 3. We just found a derivative in essentially one step. And this is what I was mentioning last time, where we're going to abandon that limit definition very quickly in favor of a much more streamlined process here. Before, you would have had to do what's x plus h to the 4th power, simplify that, and then do the limit. But now we're taking this in one quick step. So you're going to hear me say drop the power, reduce it by 1, anytime we refer to the power rule. And actually, this one's going to be a very important rule because the entire semester, we'll be referring back to this one rule. We'll be using the power rule for pretty much the entire semester. I will also note that this still works. All right, reducing the power by 1. Here we take n minus 1. So here we have 4 minus 1, giving me 3. So drop the power, reduce it by 1. You're hearing me say that over and over again. And this also works if the power is a fraction. Like if I had x to the 1/2 power, still the same process. You would drop down the power and then reduce the power by 1. And actually, towards the end of the semester, whenever we start going backwards, we're going to do a very similar rule to this. If I want to be exact, maybe I would call this the power rule for differentiation. That is the power rule for derivatives. Later on at the end of the semester, we'll talk about what an antiderivative is. All right, so clearing up the screen, let's move on. We're not going to cover the proof of this. This is just if I wanted to prove this very rigorously. If you want, you can use these formulas to prove why is the power rule true, but we're not going to focus too much on that. So let me go ahead and go through, skip those. Now I wanted to actually go straight into the example. Example 1, give me the derivative of the following functions. The first one I have is f of x is equal to 1 over x to the 4th. And the second one being y is equal to the 5th root of x squared. I want you to be careful as we work through these. Because remember, the power rule, according to that theorem, will only work so far if we have x to an exponent power. Nothing more, nothing less. Again, the power rule seems to only apply so far whenever we have x to an exponent, that is to a power. So let's go ahead and look at part A, for example. Right now for part A, I claim that I cannot use the power rule yet. Because this isn't just x to a power, it's 1 over x to a power. So don't be tempted to use the power rule just yet. But I do claim that I should be able to do a quick manipulation on this, rewrite it some type of way to make it x to a power. So looking at this, can anyone tell me what's one way that I might want to rewrite this? Not 1/4. Remember, fraction exponent means that we have like a radical, like a square root or something. But you're almost along the right track. How do I move this x to my numerator? Yeah, so remember, if I have something like this on the bottom, I can go ahead and actually rewrite this as x to the -4th power. Because that negative power means that I can take that term, put it on the bottom, or vice versa. So the reason I wanted to do this is that now I got x to a power. Hence, I can apply my power rule. That is the derivative, f prime of x. We follow the same structure. Power rule says drop the power down. So -4, I'm going to bring that down to the front. And then I reduce the power by 1. What do I get for the power whenever I subtract 1 from the power? Yeah, we get -5. Because we have -4 minus 1, we get -5. Well, we're done in a single step. Well, technically 2 steps. All right, so that one was just primarily to review about that we can move x to a power away from the bottom. Now looking at part B, let's say I want the derivative of this. Here, again, I can't apply a power rule right away because it's not just a plain x to a power. but I can rewrite this. So this one, I'm going to try to call back one old rule that you may or may not remember from algebra. How could I possibly rewrite the fifth root? It's definitely going to give me a fraction exponent. But what is that fraction exponent going to be? Yeah, so it's going to be x to the 2/5 power with a 5. So here's how we can sort of remember this. Well, not sort of, but I think a common thing that we've used before is the square root of x is x to the 1/2. These are the same expression, just written in a different way. This actually comes from the fact that here x has a power of 1, and it's a square root, like here. So really, if I want to rewrite this, I take whatever is inside, in this case the square, and make it the numerator. And then whatever the radical is, the type of root, that's going to go in the denominator. So really, the fifth root of x squared is exactly the same as x to the 2/5 power. Again, now I have that x to a power form. I can apply power rule. So getting the derivative. And I'm going to introduce one small bit of notation here. The derivative of f of x is f prime of x. The derivative of y, we often use this notation. And this still matches actually what I had on that first slide. Remember I said d dx, that means the derivative of whatever. This is quite literally saying the derivative of y in respect to x. All right, so let's go ahead and look at the power rule. So based off the power rule, I should bring down the power. So I have 2/5 in my power. I'm going to go ahead and bring it down. And then I reduce my power by 1. That is, I'm going to subtract 1 from the power with 2/5 minus 1. 2/5 minus 1. Well, we know 1 is like, yeah, negative 3/5. So we know that 1 is like 5 over 5. 5 over 5. So if I do this straightforwardly, 2 minus 5, I get negative 3/5. And then I'm done. I've applied the power rule and I found the derivative. So I'll say it again. All of these things can be proven using that limit definition we used before, but we're actually using the fact that we know the power rule and know that it's true to find these derivatives. As you can imagine, if we used the old limit definition, it would have been a little bit of a hassle to do, how do I do f of x plus h to the 4th power or to the 2/5 power, and how do I clean that up? Another small thing I want to note is I told y'all that dy dx, that just means the derivative of y, kind of like how we have f of x and f prime. Right now, where we're at in the course, I want to emphasize that this is not a fraction as we know it. This is not dy divided by dx. This is d dx. This is an expression saying I want the derivative. So in other words, don't try to multiply dx to the right as we are right now. I say right now because we go a little bit contrary to what I say later on whenever we start doing the antiderivative work. All right, so any questions about how we applied the power rule here? Again, the rule is always basically if I have x to a power, the derivative is just me bringing down the power and then subtracting 1. All right, so great. We've learned our major derivative rule so far. Let's go ahead and see what's next. So I would say you don't have to write this because we're actually never going to use this note writing here. But I'm keeping it here for the sake of formality. Let's say I have two functions. And c is still a constant. If I try to take the derivative of a constant times a function, then that's the same thing as me taking the derivative of the function, but moving the constant out. So for example, right here, if I wanted this, let's say I had f of x is equal to x to the fifth power. Someone tell me what's the derivative of that based off what we know so far? Yeah, 5x to the fourth power. This is what we've learned from the power rule. All this top one is saying is, what if instead I had g of x was 2x to the fifth power? Since 2 is just a coefficient, a constant, then it's just 2 times the derivative of x to the fifth, which was 5x to the fourth. Which is 10x to the fourth. In other words, it's saying that the coefficients are just going along for the differentiation process. So again, we know the derivative of x to the fifth is 5x to the fourth, but since 2 is just a coefficient, a constant, it's just going along, and we're going to multiply the derivative by that same constant. Again, you're rarely going to see me write it this way. Whenever we see this, you're still going to hear me say, oh, power rule, bring down the power, 2 times 5, 10, reduce the power by 1, we get x to the fourth. You're still going to hear me say that. So that's what that top rule is saying. Coefficients, they don't really change anything. We just multiply our derivative by that coefficient. The second one, it looks more complicated than it actually is. Let's say I had f of x is equal to, I'm just going to use simple ones, something like this. This is two things that are being added together. What the second line is saying is that if I want the derivative of this expression, I just take the derivative of each one individually. So if I want the derivative, what's the derivative of x to the fourth? Plus, what's the derivative of x squared? Yeah, we get 2x, 2x, 2x. And technically there's an understood power of 1, but we don't usually write an understood 1. If you want for your own sanity, you could put a power of 1 there. So that's all the second rule is saying. If you have a sum or difference, you're just taking the derivative of each one individually. Which is why I didn't want you to get too caught up on, oh, d dx of f plus minus g equal to this. That's all this was saying. We just take the derivative of each part of my sum or difference. All right, so this is our theorem here. Now let's go ahead and apply our power rule and this theorem in our next example. Oop, let's not do that one. Example 3. Find the derivative of the following functions. I'm going to walk y'all through part A, and I'm actually going to ask you to try to see if you can work through part B. I might start you off with part B once we get there. So for part A, I have P of W g of w, sorry. Again, despite the different letters, this is the same thing as if I just wrote f of x and used x instead of w. Pretty much almost all the letters we use in algebra, they're kind of arbitrary, the fact that we use x and y. Really, I can use any variable I want. So before I find the derivative, I know, based off what we know, that we're probably want to apply the power rule. But I can only apply the power rule if it's something like the variable to a power. So right now, I'm not seeing any issues about whenever I do the derivative for this first part or the second part. But I probably want to change this third part before I do the derivative. In other words, I'm going to leave the 4w to the fifth and the 6w alone. How could I rewrite the cube root of w? So if I look at the cube root of w, yes, y'all are right. It should be w to the 1/3 power. Again, we can use this idea where it's w to the 1. The 1 goes on top. It's a cube root, so that 3 on the outside becomes my denominator of the power. All right, so I haven't done a derivative yet. All I did was just rewrite it so that I can apply my derivative rule. So g prime of w. Now we're going to go ahead and find the derivative of this function just by taking the derivative down the line. So someone tell me the derivative of 4w to the fifth power. Yeah, so I should get 20w to the fourth. Again, bring down the power. So I have 5 times 4. That's how I'm getting 20. And then I do minus 1 from the power. 5 minus 1, we get 4. What about the derivative of 6w? So in this case, I'm actually going to go ahead and say the derivative of 6w is 6. I'm going to take a slight tangent to show why. I think we can agree 6w is the same thing as 6w to the 1. Bring down the power, 6 times 1, I get 6. And then we get 6 to the 1 minus 1, we get w to the 0. What's anything to the 0 power? Anything to the 0 power, any real number to the 0 power is 1. So really, this is just 6 times 1, which is why I'm leaving this as 6. The other way that you could explain this is that 6w, or 6x, that function, it is a linear function going up, the slope is 6. And what about the last one? What's the derivative of this guy? Yeah, to the negative 2/3 power. Be real careful whenever you're subtracting 1 from your fractions. Just be careful that you're actually subtracting 1. Or in this case, 1/3 minus 3/3. So we have the derivative. And again, this was without even thinking about that limit definition. We are allowed to not use that limit definition because we are taking it as our theorem that the power rule does work. All right, so great. We have part A complete. Any questions about part A before I move on to part B? So there will be a case later whenever we can't use a direct power rule. It's going to be, I'm going to say it's like a modified version of the power rule. Because right now, we know that power rule, we can only pretty much do x to a power. But what if I had something much more complicated? What if I was dividing by a lot of x's stuff? So basically, long story short, there will be issues, and we're going to see why through all these different rules. This whole unit is actually going to be how do I take the derivative of pretty much any function that I throw at y'all. But right now, we're starting off quote unquote straightforward. All right, so let's go ahead and look at B. So clearly right now, I can't use the power rule yet because it's not p to a power for each part, actually. But fortunately, it looks like I can rewrite this pretty quickly. How am I to rewrite this y of p function? Yeah, 4 times p to the 9/2 power. Again, power on the inside goes on top. This radical, whatever it might be, goes on the bottom. What about 13 over p? How might I rewrite that? I know I have 13. What happens with the p? Yeah, it becomes p to the -1 power. This is great because now it looks like p to a power plus p to a power. I can apply my power rule now. So therefore, my derivative dy dx. You can use dy dx, or there's also sometimes where you're going to see me use this notation. You might also see y prime. They both mean the same thing. Prime means the definition of y. Dx means the derivative of whatever. In this case, derivative of y. All right, so let's go ahead and apply the power rule. First one, bring down the power. 4 times 9 over 2. What is that going to become? Yeah, it should be 18. You can do this by saying 4 divided by 2 is 2. 2 times 9, I get 18. Times p to, what's the power? Yes, I heard it from both of y'all, 7 over 2. Because 9 over 2 minus 1, that's 9 over 2 minus 2 over 2. Great, we found a derivative of the first one. Next one, I do the same thing. Bring down the power. So 13 times -1, I get -13. Times p to, what's the power of p here? Yeah, -1 minus 1, we got a nice -2. All right, we're done. We found a derivative. Notice how there's very little algebra that we're really applying right now. Really the most algebra that we're applying is, I guess, more arithmetic related, like multiplying these number fractions or subtracting one. All right, so that's great. Y'all were able to do B. What about C? Let me go ahead and change the color. Here I have K of T. It's a function of T where T is my variable. And I want the derivative K prime of T. Let's go down the line and see what happens. What's the derivative of 7t? Yeah, we have 7. The power is 1. Bring down the 1. Reduce the power by 1. We get 7. Okay? What about the derivative of e squared? So as you can guess by me stopping and pausing here, derivative of e squared is not going to be 2e. Not e squared. First off, what is e? What is that value equal to? E is like 2.71 ... something like that. E squared is just some other number, 2.71 squared. So really, e squared is just a number. It's a constant. What's the derivative of a constant? 0. So this was supposed to be a trick question intentionally. E squared is a constant, and a derivative of a constant is 0, which means I'm done here. Remember, e squared, that doesn't even have my variable in there. Don't mistake e for a variable. E is a number. It's kind of like if I put pi squared there. Pi squared, that's 3.14 squared. There's not even an x or a variable in that expression. So I can guarantee that I would probably put something like e squared on a test in the distant future. And usually I get at least a couple of folks who put 2e because they're so used to power rule. But we have to remember to distinguish between a constant and a variable. All right, so we've gone ahead and done this example. Any questions before I move on? I believe there's just one more theorem and an example if I'm timing this right. All right, so let's see where we're at. Let's see, I don't want to touch that one. I guess we can go ahead and do some background on this here. So where does the number e actually come from? Just for background, because again, you've probably heard it say e is 2.71, something like that. But you don't really hear about where does it come from, like pi, or where is it used. As it turns out, e is Euler's number. That's how you pronounce it, even though it looks a little bit weird. E-U-L-E-R, Euler's number. Is the number e 2.71828 ... whatever it is, such that it fulfills this equality. The limit as h goes to 0 of e to the h minus 1 over h is 1. Again, we're not really going to use this definition, but just so that you're familiar about where does it sort of actually come from. You would probably actually talk about this more as in a future class if you took, I believe, a class called History of Math, about where does all these numbers come from. But for our class, we're just going to talk about it very briefly, about where does it come from. All right, so now this should be the thing I wanted to see. There we go. A new derivative. The derivative of e to the x is e to the x. Again, the derivative of e to the x is e to the x. Another Calculus 1 student favorite next to the power rule. So first off, I know that this is definitely different from the power rule because power rule was x to a number. But here, e to the x, we have a number to the x power. So before we had a number as the power, now we have the x as the power. Almost like we swapped them around. So let's start off with this quick example. F of x is equal to 2e to the x. What is the derivative of 2e to the x? Yeah. I shouldn't have put this prime. Well, I guess I can just fix it like this. 2e to the x. If f of x is 2e to the x, the derivative f prime is also 2e to the x. One of those things that looks like they're deceptively really nice and quick, but actually in this case it is as nice and quick as I have here. All right, so we'll do an example with this very quickly. As you can imagine, there's not much I can do for a derivative of e to the x. It's still e to the x. Do I want to cover this? No, we'll cover this next time, talking about higher order differentiation. But yeah, we have the derivative of e to the x is just e to the x. Later on as a preview, just so that I can answer some questions preemptively. Some things that we are going to take on that looks a little bit more complicated. We're going to talk about what happens if I want the derivative of x minus 3, something like that. Or if I wanted, this one's one that I like covering a lot. E to the 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 x. We're going to talk about how do we deal with stuff like that. This is actually all going to come into play about whenever we start talking about these big rules, buzzwords like chain rule, product rule, quotient rule, and trig functions and all of that. So actually this entire unit, unit 2, is going to be dedicated pretty much exclusively to here's a function, give me the derivative. Even though this is looking way ahead, like because we haven't even got to exam 1, but whenever we get to exam 2, it's actually more than likely going to turn out where I'm going to give you a big list of functions, and I'm going to say, give me the derivative for all of them. But fortunately for students, there's not really much in calculation for these sections. So if you're a person that doesn't like calculation work, going through all the algebra, this unit might be more of your preferred one. Later on, we'll talk about what do these derivatives mean and why can they help us. And that's whenever we talk about the applications exam, like optimization, related rates, and stuff like that, and profit margins and everything you can with that. All right, any questions about the material today? All right, so that's all for today. I will see y'all tomorrow.